Hello and Namaste. We are starting with the probability distributions. Under that, we are going ahead with the Poisson distribution in detail in this particular session. So we are going ahead and just taking everything related to the Poisson distribution, which are very useful for us to solve different type of examples. Starting from just to find out the lambda or mean or any probability till the fitting of the Poisson distribution. We are just going ahead with this particular one session. Now, according to the definition, if capital X is a discrete random variable, so one thing to note it down here is Poisson distribution is a distribution which is applicable or which is used when the capital X is of discrete random variable or when it is of discrete. That means assuming the value 0, 1, 2 till the point such that its probability mass function, that is PMF, it's also abbreviated as PMF, is given by probability of capital X is equals to small r is equals to e to the power minus lambda to the power r upon r factorial. R is moving from 0, 1, 2 till the point, or you can say it's till infinity. If we are aware of the point n, we can put it here. Then the lambda is always greater than 0. And probability, or you can say probability of small r is e to the power minus m to the power r upon r factorial. So rather than, so if you'll observe, if you compare these two function equations, so you can easily check that lambda is nothing but m. So few of the books are using, rather than to use lambda as a parameter for Poisson distribution, few of the books are using this small m also in the distribution. So I'm using here the different questions with different, like sometimes I'll be going with the lambda as a parameter, sometimes I'll be using the m as a parameter, just to make sure that you will get familiar with this, both the notations in the same session. Then capital X is said to follow the Poisson distribution with lambda, the parameter lambda, or symbolically capital X is said to follow, or sometimes it is also known as capital X follows Poisson distribution with the lambda or with the m. Now, Poisson distribution is also known as a limiting form of binomial distributions under few conditions. What are them? N, that is a number of trials, is indefinitely large, that is n is tending to infinity. So when we have got n is very large. Second thing is P, that a constant probability of success in each trial is very small, that is P is tending to 0. That means P is very small. That time NP is equals to lambda. NP is nothing but the mean of the binomial distribution, and this NP is same as the lambda, which is a mean of the Poisson distribution, is finite, or P is given to us as lambda upon n, and Q is nothing but 1 minus P, that is this is 1 minus P is nothing but P is lambda by n, where lambda is positive real number. So this is Poisson distribution is as a limiting case or a limiting form of binomial distribution. Now, important points to note: Poisson distribution as a limiting case of binomial means that the computation of binomial probabilities approximately by using the corresponding Poisson probabilities whenever n is large and p is small. Second thing is to note down, when an event occurs, rarely the number of occurrences of such an event may be assumed to follow a Poisson distribution. For example, the number of defective articles in a pocket of 100 or a packet of 100, then the number of printing errors at each page of a book, or sometimes the number of road accidents reported in a city per day. Now, if you'll observe here all those examples, let me just give you a few more examples of Poisson distribution. The number of faulty blades produced by a reputed firm, number of deaths from disease such as heart attack or a cancer, number of telephone calls received at a particular telephone exchange, and number of cars passing or crossing per minute. So if you'll observe here, in every of the case, you are not aware of this n in previous hand, or you can say that n is not aware of, n is not known, you can say. That means n is moving to infinity, that is this n number of trials. So that means how many defective articles in the packet of 100 we are not known of. Then the printing errors of each page in a book, we can't predict in advance or in beforehand that what should be the value of n. This is one of the way. Another thing is the probability of getting is very small in all of them. So probability might be very small, and that's the reason this type of examples we can go ahead with the Poisson distribution. Again, important notes, that is mean is equals to expectation of x is nothing but mu is equals to lambda is equals to m. I have given you all the possible notations over here. Similarly, variance is V of x is nothing but sigma square, that is expectation of x square minus expectation of x the whole square, that is equals to lambda square plus lambda minus lambda square, that is nothing but lambda. That means you can say that the mean and the variance is equal, or you can say in a Poisson distribution, mean always equals to the variance. Then standard deviation is nothing but the square root of variance, that is square root of lambda. Moment generating function of a Poisson distribution. There is one concept known as the moments of the particular function, and this is given to us as mxt, that is expectation of e to the power tx. This is nothing but this is equals to the thing. Now I am not looking at minutely for this type of notations here, as because we are completely concentrating on the different type of examples to solve. So I'll be uploading few sessions wherein I'll be discussing about the theory part of the Poisson distribution in detail. But in this particular session, I'm concentrating or I'm targeting the how to solve different type of questions based on the Poisson distribution. Then additive property of a Poisson distribution or Poisson variate. If x and y are two independent random Poisson variates with parameters mu and lambda, then x plus y is also Poisson variate with the parameter addition of them, that is mu plus lambda. Then recurrence formula for the Poisson distribution means recurrence means reoccurrence. That means if I am aware of the previous probability, we could go ahead with the next property. So this is m or might be lambda over here, but this is what is known as that means what, if I'm having this, the probability of, say for the previous value, we can go ahead and find out the probability of the next value of that particular, and it's known as reoccurrence formula for Poisson distribution. Now let us go ahead with the examples. The number of monthly breakdowns of a computer is a random variable having a Poisson distribution with mean equal to 1.8. Find the probability that this computer will function for a month without a breakdown, with only one breakdown, and with at least one breakdown. So we have to find out 1, 2, 3 probabilities using this particular given knowledge. What exactly is given to us as here? First of all, we have to define capital X. Capital X denotes the number of breakdowns of a computer in a month. Breakdowns in a month is the capital X. According to this we have defined based on the question we have been asked here and the information which has been provided with us. So mean is nothing but, so random variable Poisson distribution, mean is equals to 1.8. Monthly breakdowns of a computer is a random variable. So that is the X is this. The next follows the Poisson distribution with mean parameter is equals to lambda, which is given to us as 1.8, has been given to us in the example. Now that means the probability, or you can say a PMF, probability mass function for this Poisson distribution, gives us e to the power minus lambda, lambda to the power r upon r factorial. The value of lambda we are substituting e to the power minus 1.8, 1.8 to the power r upon r factorial is the PMF. Now first case, without a breakdown, that means what, we do not want any breakdown in a complete month of a computer. So that means capital X is coming out to be 0, that is e to the power. So that means what, in this particular PMF we are putting everywhere the value of r is equals to 0. So if we are putting e to the power minus 1.8 into 1.8 to the power 0 upon 0 factorial. Now 1.8 to the power 0 will gives us 1. Similarly 0 factorial will gives us 1, and that's the reason we'll be getting just e to the power minus 1.8. Now if you'll observe here in this case, we'll be getting the value as 0.18653 as the probability for the first case, that is without a breakdown. Second case is with only one breakdown, that is the value of x is equals to, or you can say r is equals to 1. So that means we are putting it here, the value of r equals to 1 here, the value of r equals to 1 here, we'll be getting e to the power minus 1.8 into 1.8. 1 factorial is nothing but 1, so we have not written here, and we'll be getting it here 0.2975 as the answer for this particular B case. Third case is with at least one breakdown, means what, we want only one breakdown, maximum one, or you can say at least one breakdown have to be there. So probability of x greater than equals to 1, so we want one or more than that breakdowns. What is the probability? Is nothing but 1 minus probability of x is equals to 0. This is nothing but 0.8347 is this. Actually if you'll observe here, there is one hidden step, that is probability of x greater than equals to 1 means what, probability of 1 plus probability of 2 plus probability of 3 plus probability of 4 and so on. But we are not aware of how many number of the value for n trials are there. That is the reason, that means we are not aware, so it might be tending to infinity. We can't find it out this much, all the probabilities in this series, because we are not aware of this n over here. That's the reason we have to make use of the probability, the property of probability 1 minus the probability of remaining. That is, here we have got 1, 2, 3, 4. What is not included here is probability of 0. That is 1 minus probability of 0 is nothing but this, and we have got the probability of 0 is 0.1653. So we have subtracted that from here 1, we got at 0.8347 as the answer. So we have got 1, 2, 3 A, B, C, the answers of them. Next is, assume that the probability of an individual coal miner being killed in a mine accident during the year is 1/2400. Use appropriate statistical distribution to calculate probability that in a mine employing 200 miners there will be at least one fatal accident in a year. So now if you'll observe here, we have to first understand what is given to us here in this example. So the probability has been given, that is P has been given to us as 1/2400. 1/2400. N is nothing but 200, that means 200 miners employed are placed there. So therefore M, or you can say here lambda, is nothing but N into P, that is 200 upon this 2400, that is 1/12. So we got the value of lambda as 1/12. So probability of at least 1. Probability of at least 1 means probability of 1 or 2 or 3 or so on. That means it's nothing but probability of 1. So that is what we have done it in the last example. Probability of 1, 2, 3 up to 200. That means it is nothing but 1 minus probability of 0. It's nothing but 1 minus the e to the power minus m, m to the power 0 upon 0 factorial. But we have got this m is as 1/12. So this 1 minus e to the power minus 1/12 is equals to this, and we got the answer as 0.08 probability that there will be at least one fatal accident in a year. This is what is the way you can go ahead with this type of example. Now again, they have not been given us, so it's here use appropriate statistical distribution. On what basis we have decided this is using the Poisson? Only because we are solving this under the Poisson distribution? No, it's not because of that. If you'll observe here, the probability is very small, that is it's 1/2400, it's almost tending to 0. Similarly, this n is equals to 200, so it's very difficult to follow and go ahead with the NC0 NC1 with n equals to 200. So it's very big number. That's n is very big number here in this case, and that's the reason we can easily go ahead and use the Poisson distribution over the binomial distribution for this type of examples. The number of arrivals of a customers during any day follows Poisson distribution with a mean of 5. What is the probability that the total number of customers on 2 days selected at random is less than 2? Now again if you'll observe here, m is equals to 5, that is this mean has been given to us as 5. Probability of, that is PMF, has been given to us. P of r is e to the power minus 5, 5 to the power r upon r factorial. Then if the number of customers on 2 days is less than 2, that is 1 or 2. Because other two numbers, because if you'll observe here, the number of customers can't be negative, and it will be always starting from 0. So it will be 0, 1, 2 and so on. So it's the number of customers on 2 days is less than 2. It's less than 2. So that means what? It might be 0 or a 1. So therefore first day, second day and the total. So because we have to have what is the probability that the total number of customers on 2 days selected at random is less than 2. So first day, second day and a total. If you'll observe, the first day we have got it here 0, second day 0, total is 0. First day we got it as 0, second day we got it at 1, total is 1. First day we got it at 1, second day we got it as 0, third day we got it as 1. Because we can't go with a 2, because we want it less than 2, it is strictly less than 2. We can't use it here to first day 2, second day 2 and so on. We can't use that. So we have to use either 1 or 0 customers in a day. So this is a combination what we are going to go ahead with first and second day. Now required probability is probability of 0 into probability of 0 plus probability of 0 plus into probability of 1, because we are talking here about the 2 days, so we have to take it product into it. So and it's like first day and second day, first day and second day, but this is the condition for or, this is the condition for or, and this product is the condition for and. If you'll observe here, first day and the second day, it's a combination of them. It's a combination of them. So it's a product of this into this into this probability, and this into this. So this is what we are going to get it. Now if you'll observe here, we are just putting the values over here. We are just putting the values here. We will be getting in this way. And so we are just putting the values here in R, the 0, 1, 0, 1 in this way. So we will be getting in this way here. So just a calculations. I am not going in detail with the calculations. My target is to make you understand when is the Poisson distribution case will arise and how to deal with those type of examples. These are nothing but just a calculation. Just pause the video here, try to get the answer 4.994 into 10 to the power minus 4 on a calculator. You will definitely get it. If not, please write me in the comment section. Yeah, next question is, if the probability that an individual suffers a bad reaction from a certain injection is 0.001, determine the probability that out of 2000 individuals, exactly 3, more than 2 individuals, none, more than 1 individual will suffer a bad reaction. Let us see what has been given to us. So P, the probability is very less. I mean, you can say it's tending to 0, and N is moving to infinity. It's a very large number, 2000. So again we have to make a move, and we have to go for the PD, that is Poisson distribution. M is NP, 2000 into 0.001, that is 2. So we got the value of M, or you can say lambda over here as 2. Then this PMF is been given to us as this. So e to the power minus m, m to the power r upon r factorial, taking the value of m as 2, we'll be getting in this way. Again we have to have little arrangement in this. E to the power minus 2 is nothing but 1 upon e square into 2 to the power r upon r factorial. Just an adjustment to solve the examples. Now first, exactly 3. So that means what we have to write down here, r is equals to 3. So if we're putting r equals to 3 everywhere, so it's 2 to the power 3 upon 3 factorial into 1 upon e square. The answer for this particular, just use a calculator, pause the video, get the answer, check whether you are getting the answer as 0.18, because we have to check it exactly 3. So the value of r is equals to 3. More than 2 individuals. So if I have got more than 2 individuals, means probability of 3, 4, 5 or till 2000. It's not possible to find out all of them and add them up. That's the reason we are using the property of probability, that is 1 minus probability of 0 plus 1 plus 2. That is putting the values over here. The r is equals to 0, r is 1 and r is 2. We are going to get it this particular step, which, oh sorry, just a minute, yeah, which gives us something like this, which is nothing but 1 minus 5 e to the power 2, which gives us this, and we are going to get the answer as 0.325. Again my suggestion is, come back to the step, pause the video, try to get the answer as per this screen. Then none, C is the none, that is probability of 0, and it's very simple. Probability of 0 means put everywhere r in this case is equals to 0. So you'll get it 0.135. Now more than 1 individual will suffer a bad reaction. That is more than 1 means probability of 2, 3, 4, 5 till this point. That is 1 minus probability of 0 plus 1, which is the same what we have done it here in this case, almost the same case, and we'll be getting the answer as 0.595 as the answer for this particular question. So we have solved A, B, C and D, all of them. The yellow color gives you the final answers. Pause the video, try to get the answers. Now let us go ahead and use few examples for the fitting of a Poisson distribution. Now what do you mean by fitting of a Poisson distribution? Fitting of the Poisson distribution means you have to find out the theoretical frequencies. Now these are the frequencies which has been given to you by the experiment or through the experiment. Now a skilled typist on a routine work kept a record of mistakes made per day during 300 working days. So mistakes per page or per day has been given to us from 0 to 6. Number of days 143, 90 and everything is given. Fit a Poisson distribution to the above data and hence calculate the theoretical frequencies. Means we have to find out the theoretical frequencies, or you can say frequencies using the Poisson distribution. These are the frequencies given to you by an experiment. These are the experimental frequencies. We have to find out the theoretical frequencies using the Poisson distribution. Now again, the mean of the mean number of mistakes is nothing but 1 upon 300. That is it's nothing but summation of fi xi upon summation of fi. So frequencies that is 0 into 143. It's like this: 0 into 143, 90 into 1. So it's like multiplication of these two, and our addition of all of them will gives us this, divided by 300, that is summation of fi, will gives us 0.89 as the frequencies for this, or you can say a mean of this particular number of mistakes. 0.89 is nothing but the lambda, or you can say a small m. Now if you'll observe here, we have to find out the theoretical frequencies. That means we have to find out this the probabilities of each and every mistake here. Just a minute. Probability of each and every mistake, like 0, 1, 2, 3, 4 till 6, and we have to use this PMF, probability of e to the power minus 0.89 into 0.89 to the power r upon r factorial, and multiply that with a summation of fi, that is nothing but capital N, or you can say a 300 over here. So it's very simple. Just pause the video, try to get the answers on this way. Okay, now again you have to note one thing down here, that is 123. So we are approximating it here. Just note this here. So we got the answer in the first case, that the probability of 0, or you can say frequency at 0, 123.3, but we can't go with the point here, so we have to approximate to 123. So we have approximated to 123, same as that of the numerical method properties. 109.5 is gives you 110, 49, 14, 3, 1 and 0. Addition of all of them should be equals to summation of fi, that is equals to 300. It has to be 300. All of them should get the theoretical. So theoretical frequencies and the experimental frequencies should be same in this case. Again, you can use here the recurrence relation also, or recurrence formula also, to get the frequencies. Using the previous frequency, get the next frequency or next probability. That can also be done. So quickly I'll just go ahead the same way. Fit a Poisson distribution to the following data, which gives you the number of years east sales per square of 400 squares. So this is what, again the same way. This is x, f has been given to as 103 and so on. So it's in detail I have given you here this frequencies. So if you'll observe here, frequencies has been total as 400. This summation of fi is coming out to be 529. 529 is getting divided by 400. You're getting 1.32 as the value of lambda, or you can say a mean of this Poisson distribution. Again, this is PMF has been given. We have just simplified the PMF according to e to the power minus 1.32 the value, and we got this as. Again, the same way you have to go ahead with. This is 0 till, from 0 till 10 we have to find out this all the theoretical frequencies. Again, note this down, this 107, 141, this again everything has to come to the sum, that is 400. It has to come to 400 whenever you are fitting this particular data. Again, my suggestion for you all is just pause the video, try to get this. You can use here the recurrence relation also, what we have done it in the previous case also, but I have given you both the answers in the both the ways. Yeah, and this is a self-observation slide wherein you are getting, you have got two different questions. I have given you the answers over here. If you'll note this down, I have given you the answers here. Please try to solve the examples. If you have any query, write me in the comment section. I'll definitely get back to you. I hope you have understood the Poisson distribution in detail with the perspective of the examples. Thank you so much. Happy learning.